Hi everyone, me again. So this time we are going to mess with buffers and we are slowly inching towards actual binary exploitation. Okay, so here you go. So what we basically want is we take argv1 and copy the contents to buffer, and in the process what we want is to change int x equals 0 to something that is not 0. Simple enough, right? Except it isn't. So let's get on with it. The so this might seem very naive, but yeah, this is how most vulnerabilities exist in the world. First off, remember that strcpy, as we said, is a very vulnerable function. It has no notion of how long buffer is, how long argv1 is. What it checks for is the null byte at the end of the string, at the end of the character array. So technically, buffer can only store 7 bytes, uh, and the last one being used for null. So we will try to give it an input that is larger than 7 bytes and see what happens. So first off, compile. As you can see, the same flags fno stack protector. This is useful this time. Z exit stack o0 minus g buffer dot c minus o buffer. Okay, gdd buffer. So now, first of all, we set up a breakpoint at main. So this is also sort of a tutorial on GDB and the framework that I mentioned, GEF. So both of them. So we set up a breakpoint at main, and now, so when we execute it, we usually do buffer, and then we want to put the strings. Let's say a b b b. So this is a perfectly valid string. What uh so the thing to note is there are no quotes. First of all, please do not put quotes for any reason. uh 0. Now let's say if we add another b, it's still going to be 0. If we add another b, it's not going to be 0 anymore. 98, and that's the ASCII value for b. We'll come to how that is. So the point is, in shell you invoke it this way: dot slash buffer followed by the arguments. In GDB, since you have to run it, you use R, and then whatever you do in the shell, you do here. So a b b b. So right now I'm not exploiting it because I just want to show you how GDB and this framework works in general. So I hope all of you remember the X command. If not, revisit the previous videos. As you can see, RBP is here, and this time for some reason the compiler chose to have a 32-byte large stack frame, even though we did not need it. Like int plus character array, that's like what, 12 bytes, so 16 bytes should have sufficed. In any case, I'm not judging. Maybe it needed to set up things for other functions, maybe, who knows. Once again, in any case, so first off, we see that RBP minus 0x4 is 0x0. 0x0 is being moved to RBP minus 0x4. So that means over here, once again, this is some garbage value already present, so ignore it. This will be 0, and that is our value x. So si means step into. So when I do si, it means go to the next instruction, and that became a 0, I guess. Yeah, here. Yeah. So this is our value x, and we can see that this value of RBP minus 0x20 is all zeros. Hmm. Okay, in any case, I think this is what we want. That is, so this is basically argument preparation for strcpy. RBP minus 0xc is of our interest. Why? Because it's RBP minus 12. And why 12? 8 plus 4. So these 4 and these 4 are the string. We will see we filled A, B, 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 B. So in hexadecimal that would be 61, 61, 61, 61, 62, 62, 62, 0, 0. So I will now I will use NI. So the difference between NI and SI is for any for any ordinary instruction like move, add, LEA, move, and all that, sub, both of them behave the same. But when it's a call, SI will go into the call. So you see these are the instructions of strcpy. At PLT, ignore the at PLT. Basically, it it will go into strcpy. But if I do an NI, it will continue in main. It's still in main. So SI and NI, these two are useful. So now as we can see, this got filled with 61, 61, 61, 61, 62, 62, 62, and finally 0, 0. So now if you want to continue the execution, now this isn't strictly required, but like you don't need to know it for any reason, but it's just helpful. See, just continuous execution, and you can see it printed 0. Now we want to run it again, but with a larger input, and if this time I will use different characters. So obviously this was 9 letters, so let's see what happens. Once again, into move RBP minus 0 it's 20. That would be, so this makes sense. Okay, so it, it stored the value of argv0, and argv1 would be, as you guessed, plus 8, because why? It's an array of pointers, character pointers. The first pointer will take 8 bytes. So the 0th pointer, which is the executor name, the executable name, which in this case resolved to this, would take up 8 bytes because we are using the pointer. And this is also somewhere, now I don't know how we got this. We somehow got this. So the second pointer would take up how much? Would the address would be this plus 8. And this LEA is responsible for, guess what? Loading the address of whatever is at RBP minus 0xc. So this is a hack actually. So where is RBP? Yeah, RBP minus 0xc. So this, so we take this memory and then load its address. So we are effectively loading RBP minus 0xc, the value of RBP minus 0xc. So this address, the address of this, that would be, I think C8, no, C4, I guess. That's what we are loading here in RAX. So yeah, this is one hack that is very popular in compiler design. So there are reasons why this is popular. It allows you to do faster addition and shit. Once again, not relevant, but like you should know on how this works. So we continue. So let's check the just for sanity check. Let's check the content of RSI. So as you can see, print well prints, and like slash x prints it in hexadecimal, obviously. So these are the contents of RSI. So if we are to inspect the memory of this location, what will we get? Oh, 0x. Yeah. Somehow this string stores our arguments, which kind of makes sense, right? Because CE1 is this and all. Above that would probably be interesting. Above that should be the other string. So like this is the first argument, which is which holds the pointer to this. The second argument would be 8 byte above this. I have no idea why this is. Yeah, I mean checks out, and that would hold the address to this string, this location. Yeah, so above this would be another pointer that holds the address to this location, which resolves to this string. So string is this. This is this number is what will be here. Yeah, and whatever was here got resolved because of this. I don't know how this appeared down below, like no idea to be honest, but it just did. And now we loaded the local string as well, so now we do an strcpy ni. Now call, I am doing an ni. If you just press enter, the previous one gets executed, and since I previously executed ni, again ni will get executed in gdb. So as you can see, as I said, lower to higher. So A, B, C, D, E, F, G, H, I. And if you all notice, this was our original integer x, which got overwritten with 0x69. Nice. So let's print, and as you can see, x is now 0x69. So continue, because I don't care about the rest of the execution. 105, which is hexadecimal for 0x69. If you want to verify, you can do this in Python. Once again, this is irrelevant. I just know this. There are multiple methods to do the same thing. 105 0x69, and if I have to print the character that has ASCII value 105, once again these two are irrelevant but probably helpful. So I hope this was clear. This was a very short demo of how you overflow stuff. Now let's modify the code. Which one was it? Buffer. if x equal to, let's say, 0x 2 3 4 5, printf else puts. Okay, I'll actually erase the else part because we don't need it. We just need the so gcc buffer the breakpoint at main. So this is a dummy run because I just want to see what happens, the underlying assembly mostly. So strcpy happened. Now we do a comparison. So as you all remember, this was the address for variable x. So we take the value at that address and the and the hard coded value that we had 0x2345. So basically, where is the last 1, 2, 3, 4, 5, 6, 7, 8, right? Yeah. So these two values which aren't 0x2345 right now have to be 0x2345. Okay. So I'm assuming that's fairly straightforward on how to do it. Uh, so we continue execute, and if it's not equal, then we jump to main plus 72. And as you can see, the puts call is here, which is main plus 43. So we basically skip through the puts call and main plus 72, main plus 0x7, 72 is how much in hexadecimal? Let's see, 48. So it will skip straight away here. So it will skip the puts call and the preparation of arguments in all. So these two preparation of arguments as well, it will skip and it will straight away come here, which is EAX return value of main, and by default the main's return value is 0. Once again, Beej covered it. So yeah, read Beej. That's for certain. So hmm. Uh, I think it's fairly straightforward on jump not equal. What jump not equal is doing. If it's not, you do a comparison, and if it's not equal, jump off here. Now, how that's done, there are something called flags, which, as you can see here, you do not need to worry about them much. But yeah, like you can basically assume that jump not equal just somehow checks the last compare. There are other things that can set the flags. Those are advanced triggers and advanced. There are we will cover them in something called drop chain, not now. So I think this is clear. Now I'm not showing you how you can generate the bytes. You can do whatever you want, but you know now how much to write. So you have to fill it with 8 bytes of A followed by 4, 5, 2, 3. That's what you have to do. So now control continue. No success key. So if I do a regular invocation, because most often you do not have the binary in binary exploitation, you just have to give it input. The input is what is insecure. So A, B, C, D, E, F, G, H, nothing happened. But now Hmm. So I'm not sure if this will work or not, but we can try anyways. So what I'm doing is writing 8 bytes of A, then hexadecimal 45, and then hexadecimal 23. Why 45 first and 23 next? Because we are filling in the opposite direction. So when we will be filling it, we will fill 45 first and then 23. Let's see if this works or not. It worked. Uh, so I did use Python. Now, how I came up with that snippet, it's a very painful story. It was when I was learning, and maybe I'll tell that to you in person because it's just annoying. And it has a lot to do with how strings are handled. So, spoiler alert, they are not just ASCII characters because if every character was one byte, how would you write the fancier characters like Hindi, English, this goddamn arrow over here, or my arch logo, which takes two characters. So yeah, so Python does something that forces me to write it this way. Now there are multiple methods to write bytes. I use this. So what this will do is, and I hope you all know this. If not, ask Hariboli. So yeah, cool. I think that should be good enough for this time. Hmm. Hmm. So yeah, hope you all. Okay. Okay. My bad. My bad. I forgot. I forgot. I forgot. I have to show you a good command. Uh, so now assume the since the stack over here was very small, just 32 bytes, so four double words. So you can see it, but what if it was too large? So this framework comes up has a command called hexdump or hyphen reverse. So dollar RSP. So what it will do is beginning from RSP, it will print the contents one. Now you can do let's see what happens at by word. It prints four words, but like I would prefer to have, you know, roughly the same amount of content. So make it eight. Oh my bad. I should write D word. Make it eight. Yep. So yeah. Also, one B0 is this end and not this end. I think you realize. You would realize this once you see this. One B0 is this end. So the way it will be stored in memory is the way you see it is byte. Hmm. You see each and every individual byte. Now it is one. It is one after the other. So like this is the first byte, second byte, third byte, fourth byte, fifth byte, sixth byte, seventh byte, and eighth byte. So even if you, so just in case you think it's because of reverse, even if I remove reverse, it's the same. Reverse only reverse is this, not this. So yeah, now this is in sequence. This is from B0 to B8. The reason we write it this way is because of something called endianness. Long story short, you don't need to know it. It's something hardware people came up with because they just like to be fancy. So this is something you might have to keep an eye out for, and the best way to if you cannot figure out what you should use, just see what happens. So like just now I wrote 45 first and 23 second, even though in the number 23 came first and 45 came last. Once again, NDNS. So yeah, hexdump is a very useful command. X also does the same, but dump is like slightly neater. As you can see, the output is like this is like the stack above. The stack above this, the output and layout are the same. So it's easier for you to, you don't have to mentally change context, and like it shows you offset from the value you printed. So this is pretty cool. So yeah, watch this video only after you have done GDB practice plus uh, installation of GES. That's GDB exploitative framework, I think. Exploratory framework, something like that. And yeah, that's pretty much it. Cool, thanks. Enjoy. Bye.